Exercise 10.06 is about logarithmic functions, so we're looking now at graphing the functions. Now what you can see here is I've already graphed y equals a to the x that we saw earlier in the chapter. Now what we've been talking about, how log base a is the inverse of this. And if you remember, an inverse function reflects through the line y equals x. So I've just done a dashed y equals x line up there. So if I reflect this point here will reflect to there. This point down here, that'll reflect around here somewhere. And these points that go up really high, they'll reflect that way. So our log curve ends up looking like that. That's the graph of log base a of x, which is this inverse function. Graphed y equals x is this dotted line up here. And I've graphed y equals 3 to the power of x. I'm now going to graph y equals log base 3. If you want to do this yourself, if you just do a underscore, it'll put you into a subscript, and then just arrow to the right to get back into the normal font, and there you go. And what you can really easily see here is what we learned before about inverse functions being a reflection through the line y equals x. So 3 to the power of x is this function. If you reflect that through y equals x, you do get log base 3. Okay, let's use a table of values for the same result. So remember, log base 3 of 3 to the x, the log base 3 and the 3 cancel each other out. That's just equal to x. So here where I've got 1 over 9, that's the same as 3 to the negative 2. So if I take log base 3 of 3 to the negative 2, I'm going to get negative 2. This one's power is negative 1. This one's power is 0. That's 3 to the 0. This is 3 to the 1. This is 3 squared, and this is 3 cubed. So as you can see, the power ends up being the answer for log base 3 here. So I'm going to graph those values now. So when x equals 1/9, y was equal to negative 2. So 1/9 is way down here, down at negative 2, there's the point there. When x equals 1/3, our y value is negative 1. So 1/3 still down here. I'm still pretty close to the axis there. When x equals 1, my y value is 0, so that's around about there. I might just put a little one there because that's quite an important point. When my x value is 3, my y value is 1. When my x value is 9, so I'm now way over here, my y value is 2. And when my x value is 27, my y value is 3. So one of the things that you'll see here is that it does climb quite slowly, where an exponential curve climbs very steeply, very quickly. A logarithmic curve is a much slower kind of a growth, but it does go to infinity. So the domain of that, it never touches 0. So rounded bracket from 0 to infinity, because it will keep going this way forever. The range is that y, it does go down to negative infinity, and although this climbs very slowly, it does still go up to infinity. So negative infinity up to positive infinity is the range. To look at some transformations of the log function, so I've graphed here log base e of x. So if x was e to the 1, or about 2.7 to the 1, my y coordinate would be 1. And we can see that right around here. When I'm at about 2.7, I'm just under 1. 2.71 is pretty close to 1. Remember, it was about 2.718. If I zoomed right in on that, I'll be able to see that point where my x is e and my y is 1. But you can see it's around that point. Okay, let's look at what happens with this curve when we reflect it through the axis. So if I put a negative in front, have a think, is that going to reflect through the y-axis or the x-axis? There you go, through the x-axis, just like with other curves. If I put a negative in front of the x, it does reflect through the y-axis. So that's just like with other curves. If I add 3, it shifts up. If I minus 3, it shifts down. So just like the other things that we've looked at. Now the other thing I really wanted to show you is what happens when I zoom. Remember I talked about this log curve increasing to infinity, but very, very, very slowly. So if I zoom, you can see how close it looks like it is to the x-axis. I'm actually going to change the values of my axes. So I'm going to make my y-axis go from, say, -2 up to, say, 5. And I'm going to make my x-axis, the biggest number on my x-axis, I'm just going to put in a bunch of 9s. Oh, too many. Okay, let's just go a little bit higher on the y-axis and put in another 9. Okay, so you can see here when x is equal to 7,000, my y-coordinate is barely less than 10. Now, just to compare, I might just look at what log base 10 is. Now, log base 10 on Desmos, you don't need to put a base. It will read that as base 10. You can see it's a lower curve, but the same shape. If I was to, say, add 5 to that, you can see it's not the exact same curve. It does have different steepnesses at different points. They actually cross each other right here at this point. It looks like 0, 0, but that's just because of how zoomed we are. It's just approximating as 0, 0. It does not touch 0, 0. Okay, so I might just look at the zoom on the, let's just focus on the blue one, log base 10, and just increase my x value even more. So you can see with log base 10, when I have 8 times 10 to the power of 10, so what's that, like 800 million or something? My y-coordinate is still barely over 10. Now, it does keep going. It does keep going to infinity. If I zoom even further on my x, so let's just put a few more 9s in there, you can see it looks like it's going up and up and up and up and up. And it will keep going up. So it does go up to infinity. It will keep going up and up and up. As my x gets bigger, my y will also get bigger. Okay, I'm just going to do an example where I'm going to graph the curve y equals 2 log base e of x plus 3. So in order to do that, we know the basic shape. We know that the y-axis is going to be an asymptote. We know it's going to have this general shape. Because of that times 2, it can, and it's going to change the steepness of it slightly. The plus 3 is going to shift it up a bit. So that will actually, the plus 3 will actually change the x-intercept. I have decided to put 1 just here. 1 is always a nice number to plot because log base e of 1, or log base anything of 1, it's going to be 0. So 2 times 0 plus 3, so that's going to come in there at about 3. So that's going to be the 0.13. Just to keep things simple, I'm not actually going to put a scale on my y-axis at all. I just really want it to be nice and simple. I wouldn't even need grid paper really to do this. Now, the other thing we do need to find is an x-intercept. We don't have a y-intercept, as I said, it's an asymptote, but let's find the x-intercept. So remember, the x-intercept is when y is equal to 0. So if I set y equal to 0, then I'm going to have 2 log x plus 3. Notice I've just done the ln because it's the natural log, is equal to 0. So 2 log x equals -3, subtracting 3 from each side. Divide by the 2, so log x equals -3 on 2. X equals, so to undo this log, I need to do e to the power. So it's e to the power, 3 on 2 is 1.5. Just for the sake of space, I'm going to write it as -1.5, but it could be, I could have written -3 on 2, that's fine. And if I put that in my calculator, that's approximately 0.223. I'm going to mark that x-intercept on my axis here. So that's somewhere between 1/4 and 1/5 of the way along. 0.2 would be right here because that's 1/5. So about there is my x-intercept. And I'm going to put e to the -1.5 next to that to label it accurately in exact form. And then using those 2 points, I'm just going to draw a log shape curve through those. And that's quite sufficient in terms of graphing. You've got 2 points, so you've given some scale, you've given the general shape. It's clear there's an asymptote, but it would be better if we did a dashed line up there to show that it is an asymptote. In this example, I'm going to find the inverse function of y equals log base 5 of x. Now, we can just use what we know about power laws, but I'm going to do it the way we did it in the previous chapter on finding inverse functions. So remember, the first step was to switch the x and the y. So x equals log base 5 of y. And then I'm just going to take 5 to the power of each side. So 5 to the power there, 5 to the power of all of that. So this side is 5 to the power of x. 5 to the power of log base 5 cancels out, and that side is just y. And I'll just turn it around. Y equals 5 to the power of x. Okay, in this example, we're going to look at what's called a log scale. So I've graphed log base 10 of x over here like we're used to seeing it. But what I've given here is a log scale. So as you go across one, I've done it to the same units as this. So 1 unit up there is 2 squares. So I've gone 2 squares across, and that actually, instead of going up 1, it multiplies by 10. And this is what we call a log scale. So one thing you'll notice is I haven't actually drawn a y-axis here, because it kind of doesn't make sense to, because this would be 1 over 100, this would be 1 over 1,000. You never actually reach the y-axis, but I am going to use this scale over here. So you can just use a calculator if you want, but remember it's the power. So log base 10 of 1 on 10, that power is -1, 10 to the -1. So if I graph -1, that's down here. Log base 10 of 1 is 0. Log base 10 of 10 is 1. Log base 10 of 100, well, that's log base 10 of 10 squared. So that gives us 2. You can see here that we're actually getting a straight line. Log base 10 of 1,000, that's 3, because it's like 10 to the power of what number equals 1,000. So we do actually get a straight line when we graph a log with an x-axis as a log scale. It's also possible to use the y-axis as a log scale as well. In this example, I've set the y-axis as a log scale, but base 2. So every time you go up by 1, you're doubling it. Or if you're going down, you're halving it. So again, it doesn't make sense to have an x-axis this time, but I will use 2 squares as the count of 1. So I'm graphing y equals 2 to the x. So if I graph y equals 2 to the power of 1, that's 2. So if my x is 1, I'm in this column. 2 to the power of 1 is 2. If my x is 2, so 2 to the power of 2, well, that's 4. If my x is 3, 2 to the power of 3, that's 8. If my x is 0, 2 to the power of 0 is 1. If my x is -1, 2 to the power of -1 is half. So you can see, once again, I get a straight line. So if I use this log scale on my y-axis, I can turn an exponential function into something that looks linear, because the axis is not linear. And I can turn the log one in the previous example into something that looks linear by having a log scale on the x-axis.